Welcome back, everybody. This is the second session of Gridlab-D training for developers. In the first session, we did a general overview of the tool and some background information on the theory of how Gridlab-D operates and its history. We also spent some time talking a little bit about the Gridlab-D environment, the modeling language, and the kinds of tools that are available. In this session, we're going to go into a lot more depth, following up on the homework assignment that we had in the last session, which was to install the software on your system and attempt to do a build. As we go forward through this, I think what we'll do is we'll try to answer a lot of the questions that typically come up and give you an overall background on how to do how to build the software, what the process you have to follow is to get it validated. So first thing I want to do is just give you a general orientation on the GitHub repository where the software is currently stored. In this overview, I'm going to generally try to illustrate how things are done given the current environment that we have. That environment is changing over time. What you'll find is there are certain repositories that are forked from other repositories, and those may change later in time. So I suggest that even if you were following this session and using it as a guide for how to do things, that you be observant about what the current status of the software is, because at some point in the future, things may change a little bit. So you'll notice, for example, in these pages right now, the HiPAS organization in GitHub is forked from the Slack Gizmo. And at some point in the future, that's going to swap, and Slack Gizmo will be forked from HiPAS. So those are the kinds of little details that may, at some point in the future, trip people up as they watch this or follow these slides. So I just want to draw your attention to that before we get too far into this. Generally, there are two pages that are important when you are trying to install and run Gridlab-D. The main page that you land on when you go to the Gridlab-D repository for HiPAS is the README file, and included in that README file is a developer quick start. It's very brief, but it has some of the key steps that you have to follow to get your system installed, and I'm assuming that's what most of you followed when you tried the homework assignment from the previous session. There's also a wiki tab that's on the GitHub repository that has much more detailed information about how the development process works and how you build and manage your code on your system. That wiki page is not for users, that is strictly for developers, and it has just general information about how development is done on HiPAS Gridlab-D. The documentation for users is actually stored in the documentation in a separate documentation tool that's at docs.gridlabd.us. User documentation is branch sensitive. So in GitHub, there are multiple branches of Gridlab-D. Each branch has its own documentation. The developer documentation is not branch specific. There is one documentation for all branches, and that version of documentation is meant to always remain current, and that's what developers should follow. Just some quick statistics on the Gridlab-D source code base. It's fairly old software. It was developed by a large number of contributors over a long period of time. The first contributions to the repository that's currently in GitHub came in through Subversion, and that was back in 2007. It was on SourceForge, and when the SourceForge repository was moved to GitHub, all of the history that was in the software going all the way back to 2007 was copied as well to GitHub. So we do have a lot of the old history that's still available, including the contributors going all the way back to 2007. Some of the oldest code in the software actually predates that by about 10 years. I believe the unit manager that's in the core engine comes from code that was developed back in 1997. Overall, the code base has about more than 800 C++ source files. totaling about 350,000 lines of code. Recently, there's been a lot of Python code added, totaling maybe 200 plus files and almost 50,000 lines of code. In addition, there's a huge number of Gridlab-D models, GLM files and supporting files that are used for validation testing, totaling almost 3 million lines of code to validate the system. So all told, there's a significant number of files and lines of code that go into the software itself, most of it coming from PNNL, with a fair amount of additions coming from Slack and other contributors over the past 5 years. The software supports a number of different platforms, most of which I think are the common platforms that we find people using. A lot of the work at Slack is done on Mac OS, Intel type of platforms. The more recent M1 platforms are still being worked on. Most people run in a Linux native environment, even when they're running on other platforms. And we'll talk about that in a little bit more detail when we get to that point. The most convenient way to run it is actually on Docker. So Docker is a very well-supported environment for getting Linux environments, in fact, other environments running on just about any environment. And what's really nice about the Docker platform is it allows us to ensure high repeatability. We can get the same software running on different systems in an identical environment and have some assurance that we're running exactly the same system, even if we're moving from one platform to another. Amazon AWS is another environment, a lot like Docker, where we can ensure high repeatability in the results that we get from the software. And in addition, you can run in Microsoft WSL, which is a Linux platform within the Microsoft Windows environment. And all of these are very flexible and run very efficiently. And Gridlab-D works fairly well in all of these. Overall, the procedure, there's a fairly lengthy procedure you have to go through. You have to prepare your system to be able to even download and install the dependencies on the system. Then you have to install Git and the other dependencies, libraries, and install build tools. You have to download the source code itself. Then you have to configure the build the system, and then finally you can validate the system. So what we'll do today is we'll go through all of these steps in great detail. And hopefully by the end of this session, we'll have answered all of the questions that you might have in trying to build the software, and you should be more successful at building it in the future. So the first step is to prepare your host system, and the process that you go through depends on the system that you're running. Generally, if you're running on a Linux platform, it's pretty much the easiest platform to build on. This includes if you're running in Docker. And to some extent, it's true for Amazon AWS, but there's a few steps that you have to do in AWS first before you can get things sort of in the standard Linux way of building. So you have to update your installer. So typically we use Git, and so you have to make sure that Git is up to date before you do anything further, and then you install Git itself. I'm sorry, not Git. Your local systems installer like Yum or apt. You have to make sure that's up to date before you install Git. When you're running on Mac OS, the most convenient way to do this is to install a tool called Homebrew. And if you go to the Homebrew website, it has instructions, and we'll go through that later, but it has instructions on how to get that installer on your system. And then once you have Homebrew, you can install Git and go through the process that we'll go through later. On Windows, you have to start your WSL environment. If you haven't ever done that before, it may require a reboot of your system. The WSL environment gives you the ability to run Linux software on your system. Then you update the installer for your Linux system. So if you're running a Debian system, it has, I believe it uses apt, and you have to update the installer, and then you install Git itself. On Amazon, you have to launch an EC2 instance. So you log into your Amazon console, and you go to the EC2 service, and you launch an instance, and then again, update the installer and install Git. And that is basically what you need to prepare your system for all of these different platforms. So let me go through this in a little bit more detail for each of these. For a Linux system, depending on the system you're on, you may have to run sudo. There are some hosting environments that when you run them, you're already a super user. So you don't have to do anything you have to tell it that you want to be super user. There are other systems where you should not be super user. So you kind of have to know whether or not sudo is going to work. Generally, what I do is I first try it without sudo, and if it doesn't work, tells me I have permissions denied, then I do it with sudo. So for example, on a Mac, brew does not like you running it as sudo, so you should probably not use it. But on other Linux environments using either yum or apt, generally, if you're not already super user, you may have to run as super user. I don't like how verbose update is, so I just tell it to be super quiet, which is what this -QQ option is. So unless something goes wrong, I don't want to hear about it. So if you just put this QQ option when you do the update, then it'll just run quietly. And generally, there's no reason why anything should go wrong unless you have network issues or some server is down or something. Once you've updated the installer, you can install Git, which you will need to proceed. And generally, again, same rules apply with brew, yum, and apt, and whether or not you need sudo. And then you just ask it to install Git. You can tell it to run quietly. I generally do. And if you put the -Y option, that basically means answer any question it asks with the answer yes. So if you're concerned or you want to be sure that it's doing what you expect, don't put this in. If you're confident you typed the command line exactly as you wished it and you're not worried about anything, then you can go ahead and put that -Y option to tell it to just proceed. On Microsoft Windows systems, you need to be able to run WSL. So if you have older Windows systems, you may not be able to run it, or you may have a more limited version of WSL. But the most recent Windows systems work very well, and you just need to open PowerShell as an administrator. And then once you have PowerShell running, you can run the process of setting up the WSL environment. I strongly recommend you use the Debian 11 distribution. I know the others do work, but the Debian 11 is the one that we've tested and used most frequently, and so it's the one that we have the highest confidence in. I'm assuming that they're more or less equivalent anyway, other than if you already have a preference for another one, you may be more comfortable using Ubuntu or one of the other Linux distributions. Someone's asking whether there's a space requirement for the installation. It's not a large space requirement. The source code itself is probably, I'm trying to remember exactly how much it is. It's a couple hundred megabytes. It's not particularly large, but it's larger than the typical source code. When you build it, though, it does create a lot of auxiliary files that are pretty large. Generally, I recommend that you have at least 4 gig of disk space to do the build, another maybe 20 gig to do validation processing. And in terms of RAM requirements, I've been able to do it on T2 micros. It's pretty limited, but you can run on T2 micros on AWS, which is, I think, 1 gig of RAM. My own personal preference is to have at least 4 gig of RAM on the system. Yeah, it does have a fairly substantial footprint in memory when it's running, particularly if you're running parallel, which you're able to do. So for example, if you're running 8 processors, you should have ample RAM for that. Maybe 32 gig of RAM would be a good amount available to those 8 processors. When you're starting to run up in very large numbers of processors, which you can do, you're going to have very large memory requirements. And so that, yeah, once you completed the WSL installation and you've got your Linux environment running in Microsoft, then you just continue with the standard Linux preparation for whichever Linux distribution you chose. On Mac, as I said earlier, I strongly recommend you use Homebrew to do the installation of everything. In fact, I think if you do automatic installs, you have to use Homebrew. If you do things manually, you could probably get away without Homebrew, but I really don't suggest doing that. It's very difficult. Homebrew really does make things very easy for you. And it's a nice environment, and it does do excellent housekeeping for you. So that's definitely a good way to proceed. The command line is too long for me to put on there. If you go to their website, they provide it to you. And it has always worked for me. So I've never had any problems with it on Intel environments. I will caveat that on an M1 environment right now, it can be challenging. Not everything works yet on M1. Once you've installed Homebrew, you should either verify that your current Git, whatever's already on your system, is a good version, and if necessary, install the correct version of Git. And then proceed. You can proceed with the standard Linux installation at that point. Everything should be the same from then on. On Docker, there's a tutorial actually for using Docker on a Mac, which is where we most typically use it. It's really not necessary on Windows because WSL is essentially the same thing. Once you've installed Docker and you got it running, you can just open a terminal on your system and start the Docker instance that you want to work with, and then continue with the Linux installation at that point. So this is for building from scratch. There are actually Docker images pre-built for different versions of Gridlab-D, including the development version, which you can use instead of building straight from the Debian 11. And so if you look at the Gridlab-D repo for HiPAS, you'll find instructions on which version, which images are available. So there's a variety of images available to users so that you don't have to go through the whole build process yourself. But as developers, typically we want to start from a clean build and verify that everything works from a base system, because that's how we build the actual systems that we make available to everyone else. So this is the first step in doing that. Afterwards, then you continue with the Linux preparation. If you're running on Amazon, so you just start an EC2 instance. We've tested a very wide range of instance sizes, and most of the useful ones have been tested. We haven't tested them all. That would take some time. But we've gone everything from T2 micros all the way up to 24x larges on C5A. So we've done a wide range of EC2 instances, and it works very well on all of those. So once you've launched your EC2 instance, you can just proceed with the standard Linux preparation from that point on. So as I said, there are some all-in, just sort of, all put together I guess you'd say pre-canned installation scripts. If you clone your repository from this Gridlab-D source, then you can simply run the installation script, and it will actually do all of the work that we're going to talk about today, if it can. On most systems, this installation script can identify what needs to be installed and run the proper installation procedure. That process can take quite a while. It could probably take as much as 10 or 15 minutes to run through the entire process, maybe even more, depending on your system. And if the process fails, then you have no choice but to run through the manual process that we're going to go through today, which can take quite a lot of time, especially in a system where it's not been run successfully before, and you may have to figure out why it's not able to build on that particular platform. So this automated process, the Gridlab-D install.sh, is basically a shortcut for everything that we're going to go through today. And so you really only need to run through that process manually if it doesn't work. All right, so If you have to run the process manually, this is the first step of that manual process, or the second step of the process overall. So first of all, there are a lot of system dependencies or system-specific things that you have to do. And it's not a bad idea to look at what the script says for your particular system, and even if it didn't work, or a system that's very similar to yours. A good example is, for example, so if you're running on Monterey, which is Darwin 21, you'll find there's no script for Darwin 21 yet. So if you're to run the manual process on a Monterey system, it would tell you, I don't know how to build for Darwin 21. Well, what you could do is you could look at Darwin 20, which is very similar, and just follow the steps in the Darwin 20 script and run through that process manually. And if there are no problems, then it will simply proceed and it will work properly. Another trick you can do is actually make a copy of the file that has the appropriate name. So for example, if you take the Darwin 20 script and you make a copy called setup-darwin-21 and then rerun that original install.sh script, it might work. In fact, on Intel systems, it does work. So you can do that fairly easily. If you encounter a system that's not in the scripts, then you're welcome to make a copy. And if it works, you can submit that to the repository for us to review and include in future code downloads that other people make. So this is, of course, potentially a very valuable contribution that you can make. In any case, when you run these scripts, be aware that it is changing your system and potentially in important ways. So the usual advice that everyone always gives is make a backup of your system before you do that. So there are a lot of changes being made, libraries being added, versions of software being updated, and so on and so forth. And some of those might affect the way other things work. So you should be aware of that. Overall, what this script does is it installs all the build tools that you'll need, the GNU tools that are used for compiling and making software, the libraries that are used to create the application itself, and a lot of the services that support the application once it's up and running. And all of those will be downloaded, built, and started up on your system in order to ready your system for Gridlab-D. And again, like I said, that all should work fairly smoothly. There shouldn't be any problems, but it can take quite a while to go through all of those steps. Just to give you an idea of what's being included in that process, obviously we mentioned already Git is used to access GitHub. Unzip is typically required as well to decompress files that are downloaded. Most systems come with Unzip already installed, but not always. And so you may have to install that tool as well. And then, as I said, auto tools, so autoconf, automake, libtool, and then another software make process or program called CMake is used by some of the tools that are dependent or that Gridlab-D is dependent on. Another thing that is necessary is on some systems, the stream editor is not the correct version. And so we require that you upgrade your SED software, the SED program itself, to the GNU version of SED. We also require the GNU version of awk, which is a parsing tool that is used to produce some of the files that are needed. So that has to be installed. And we require that you use a custom build of Python 3.9. It will not work if you just download the generic version of Python 3.9. You must use the custom build that we provide, that we require with Gridlab-D. And that process of building and installing that custom build is included in the scripts. It's installed in a way that should not intrude on other Python 3.9 installs on your system. So you can use Python 3's mechanism for controlling the priority of Python 3.9. But once that special version of Python 3.9 is installed, Gridlab-D will use it regardless of how you set your priority on other Python 3 installations. There are also a number of documentation generation tools that are required. Currently, 3 of them are necessary if you want to build a documentation. The reason they're italicized here is you don't have to install them. If you don't, it simply won't generate the developer documentation, which is not that bad. It's not a problem because most of that documentation is available through other means anyway. But Mono, Natural Docs, and Doxygen are all used at some point or another during the build process to create all of the developer documentation in the software. A lot of libraries are also needed. Most of them relate to getting files online using curl or decompressing files that are downloaded. There's also a library that's needed for a couple of features in Gridlab-D that it's called curses. It's basically the tool that manages how the cursor moves around the screen in certain applications that are basically text oriented in the shell. And then on some platforms, you need some Linux utilities. And then in order to run with a lot of database driven tools, including the sign converters and other types of software that require access databases, MDB tools also needs to be installed. And then finally, the Python installation has a lot of requirements that have to be supported as well. So there's a lot of libraries that need to be downloaded and packages for Python itself. And those are all listed in the requirements TXT files that are scattered throughout the source tree. The next step that you do once you've gotten every dependency installed on the system is to download the software itself. The easiest command that you can do for that is just to clone the source itself into a Gridlab-D folder. That will just clone it into the current directory in a folder called Gridlab-D. Alternatively, if you've already downloaded it, then you could just do a git pull to update, get the latest changes. I strongly recommend as developers that you always get the latest changes. In fact, the best thing to do is just do it every morning because there are many changes happening on the development tree. It's a fairly frequent thing to have new versions posted or updates posted and changes made from pull requests into the develop branch itself. And so if you don't follow the develop branch closely, your branch will diverge quickly, and it may become very difficult for you to do a pull request or to merge later. So you want to keep up with that as much as possible. The branch that you're working on, for most developers, it's typical to start with the develop branch and then create your own branch from that. You can start from the master branch. And of course, if you want to know what people are using right now, that is the one to check out and build. That's, if we get an issue, for example, the first thing we'll do is test and try to repeat the behavior of the issue on the master branch. And then if we encounter that problem, we then will try to fix it in the develop branch. So the master branch is protected. And so the changes that you see on it are rather infrequent. They might not be more than once a month, possibly every few months. And if you just want to see what the status of your branch is, of course, the git status command lets you know which branch you're on and what changes you've made relative to the branch that's on GitHub. Just a quick orientation around the source tree itself. There are a lot of auto test folders, including one in the root in the project folder itself. It contains all of the taxonomy networks that we use for testing. The taxonomy networks were developed at PNNL some years ago. They provide a very good cross-section of the kinds of feeders that you find in North America. These are used to test Gridlab-D's solver, and the PowerFlow solver in particular, and make sure that it's working properly, because we know what the solution should be on those feeders for the conditions presented in the auto test. A lot of other folders also have auto test folders within them, and we'll talk a lot more about how the auto test folders are used in validation. The build aux folder we've mentioned already contains a lot of the setup files that are used during the installation process. And it's one that you frequently have to consult when you're getting your system ready. Once your system is readied, you generally don't need to look at this folder ever again. It's not something that you would normally look at otherwise. The cloud folder includes all of the folders needed to deploy Gridlab-D on various cloud systems. And right now, primarily the focus is on the S3 buckets in AWS that support all of the URLs that are used by the software, the documentation, the tutorials themselves, and a variety of other websites that are deployed by Gridlab-D. Those are maintained here. The converters contain all of the automatic converters that Gridlab-D supports to bring files in and out of Gridlab-D while it's running. Docker contains all the files needed to build the Docker images. Docs contains all the online documentation for users and some developer documentation, but it's quite limited. That documentation is branch specific, and we'll talk about this more later. But I mentioned earlier that the developer documentation is not branch specific, but the user documentation is branch specific. And so when you make changes to a particular branch, you should make the changes in the documentation with the expectation that as your changes in your branch get merged into develop and eventually into master, that the documentation will be updated accordingly based on what you put in your branch. There are additional documents. They tend to focus on sort of the engineering support of the specific tools that are in Gridlab-D. There are not a lot of these in here right now. They're still scattered around in some cases in the modules themselves. We'll talk about those in a minute. But most of these documents are not for users or developers. They're for sort of the engineering support team that does a lot of the analysis and modeling work that then goes into the developers' code contributions. Doxygen is one of the tools that's used to build documentation for developers. And this is basically the configuration files that are used by Doxygen to generate that source documentation. Geodata contains all the packages that have geographic capabilities. So basically all the packages that use latitude and longitude as part of their data processing. And there are, we'll talk about those a little bit more in future sessions, but all of those packages are included in the geodata folder. M4 is basically some files that relate to the configuration process and building Gridlab-D, not something you generally need to look at or touch. The modules are the Gridlab-D modules themselves, and there are quite a few of those, and we'll talk about those at much greater length in future sessions. Those modules can include a lot of C and C++ code that's used to construct the classes that are used by Gridlab-D when it's running. And so there's a lot of code and a lot of implementation in these modules. In fact, the bulk of the system itself, Gridlab-D itself, is implemented in these modules. Python is the Python link to from between Gridlab-D and Python itself. So it's the source code of that linkage. Python 3.9 is very tightly integrated into Gridlab-D. Gridlab-D can call Python, Python can call Gridlab-D. Those two have been linked together sufficiently that we can pretty much do just about anything that we want in Python that we used to be able to do only in C. So the Python linkage is quite effective at allowing us to avoid having to implement stuff in C and C++ as modules. Python externals is just a bunch of a collection of tools that have come from various organizations that have done a lot of work in Python and Gridlab-D. Python extras is just other stuff that's not organization specific that is available for people who are writing Python code for Gridlab-D. Runtime is the folder that contains all of the support resources for Gridlab-D when it's actually running on your system. So there's a lot of things like images and the units file and the time zone file and other stuff like that that's required when Gridlab-D is running. And these files are maintained in this runtime folder. Source is the actual source of Gridlab-D's core engine. It includes, I don't know, a few dozen C++ files and some C files and all the supporting headers and libraries needed to get to build the Gridlab-D engine itself. That engine is what loads up the modules and the Python code and links everything together. The subcommands are all the newly introduced subcommands that are part of the HiPAS system. These were not part of the original PNL system itself. These subcommands were added to allow us to do things like manage weather data, libraries, and templates, and all of the support tools that are needed to manipulate the caches and local copies of software that are used as part of Gridlab-D. Third party contains all of the libraries that are needed to build Gridlab-D. You generally don't have to touch any of these. They're built as automatically as part of the build process. We're trying to get rid of these, but at this point, there's still a couple that we require and these have to be built at the same time that Gridlab-D is built in order to ensure that we have exactly the right version running correctly on the platform that you're running. Tools contains a lot of other Python and shell scripts that work similar to the way subcommands worked, but they're not really as tightly integrated as subcommands. So there are things that allow you to do things like download weather data or download wholesale energy market price data and things like that. So they're not quite in the same category as geodata or subcommands, but these are very useful tools that have been developed during the course of creating the PNL version and the CEC version of Gridlab-D. And so they've been packaged up and delivered in a manner that's similar to the way subcommands work. Tutorials are sort of the non-developer tutorials. So we've been producing a variety of more general tutorials, and those are being deployed in the tutorials folder. Those will eventually work their way into the tutorials website once they're completed. And I think once we're done developing all these tutorials, we've integrated everything, this folder will probably go away because it will be included in the cloud websites folder for all the tutorials, and there won't be any need to have them here anymore. And then utilities are just a bunch of utilities that are used to help manage your build and so on. So yeah, there's a lot here. And as we go through this session, you'll see that we'll talk a lot more about these. Okay, so now that you got your software downloaded, you got all your source code, you need to build the system. And the first step in building a system is to run autoconf. My favorite way of doing it is to simply assume that I've already done it and then just tell it to deal with it. So that's what these options do. It basically tells it to go ahead and reconfigure the system, which is implicitly configuring it if it's the first time. And this basically just tells it to force it and ignore errors, just do it. It gives you some noisy output and things that you'll see some errors, but none of them generally are much of a problem. It's almost always successful at doing it unless there's something really, really wrong with your source tree. And then once it's done, you can proceed to running the .configure, which is one of the files that this autoreconf creates. I want to just mention one caveat. There is one file in the Gridlab-D tree that if you change it, you will have to manually rebuild its output, which is gridlabd.in, and that's in the source folder. There's almost never any need to change this file, but if you do and you don't manually update, it's possible that the reconfiguration, this autoreconf, will fail, and it won't work until you redo this manually. Unfortunately, there's been no way for us to fix this problem. We haven't really, I have to confess, we haven't tried really hard to fix it because it's so unusual that you need to change this file that we don't generally run into this problem. And there's a comment up at the top of the file that if you open it and you start editing, it'll tell you that you need to run this particular command. So you'll find the command that you need to run on the first line, but this only happens if you happen to edit the M4SH file for Gridlab-D. And just FYI, this is the thing that actually creates the run script that Gridlab-D uses when it's installed on your system. So when you type in Gridlab-D, this is actually what it's running. And what it typically does is just checks your system out and makes sure that the binary is correct and does a couple of housekeeping things before running the actual executable. So once you've built your make file, once you've built your configuration file, you run it. Again, it's a very chatty program. It produces a lot of output. The final block of output is actually pretty useful. It tells you a whole bunch of things about what it did and how to use what it created. And in particular, it will tell you where it intends to install the software, what options have been found and enabled, what things didn't work. And so that's quite a useful block of output. You can also give it some options. So for a lot of developers, there are flags that they like to set to enable debugging and things like that that can be useful to set. And then a lot of people like to quiet configure down. And so if you include the -- silent, that'll get rid of this really noisy output. But these are the two required steps to get everything ready for you to build the software on your system. Once you run these two steps, you don't generally have to redo them unless you change branch or do a merge from another version that would change the build version number on the Gridlab-D itself and such. So typically you don't need to do this, but if you do a git pull or a git checkout of a new branch, then you will need to. Once you've run configure, you can run make, and that will take quite a while. There's several hundred files that have to be compiled. That process, you can actually implicitly do that if you want to just go right ahead and install. If you're confident it's not going to give you any errors, you can just go ahead and do a make install or a make system. And I'll talk about the difference between make install and system in a minute. Yeah, running make just compiles it and does not install it. Running make install will create an installation copy, but it won't link it to your system and it won't make it part of your path. Make system will actually link it to the system itself and make it the default installation on your system. As I said, if you change any settings or you change a branch or anything like that, then you need to reconfigure your system, your build. One way you can do that is you can actually just type make reconfigure, which basically just runs the auto reconf and configure commands again. One thing I like to do is in the morning, immediately after I do a git pull and I make sure I have the latest, I just do make reconfigure and the double ampersand and make system. And I just make the latest version my system version. So that's a convenient way to sort of run the whole process quickly for your first time build in the morning after you do an update. So as I said, the target install will install the new build of the software in user local opt Gridlab-D. So this is the standard location for Intel builds. By the way, I mentioned earlier M1 does not work. One of the things M1 won't do is it will not install in user local. That's simply not how it works. So if you're running on an Intel Mac, that's fine. But if you're running on an M1 Mac, it's not going to work. And as I said, we haven't got it working yet. We're still making sure that M1 builds properly, and we have not resolved all of the issues. Some of the libraries are not available yet for M1. If you target instead system, then what happens is that it does the install to user local opt, but then it links everything to user local bin, lib, share, etc. There's a whole bunch of folders that are linked. And that install becomes the system install. So all users on the system will see what you just built and installed. The naming convention for the files that get put into user local opt is essentially the version number, the build date, so it's year, month, day, and the branch. And so as I said, if you change branch or you do a checkout that changes the build date or changes the major, minor, or patch number in the version, then you're going to have to do a make reconfigure, because anytime this version name changes, you have to reconfigure. Once you've done that, then the install will create a new copy of the newer version in the user local opt directory. That means, what the implication of that is, the old version is still available, and you can actually use the Gridlab-D version command to see what's available, to show what's currently set, and to change it. So you can change your system's version just by using this command version. This is a sub command version. So you use the sub command Gridlab-D version set, and then you can either give the actual name or a pattern that uniquely identifies which one among your list of available versions is the one that you want to use. Basically what it's doing is it's creating a link current to whatever version you set, and then the system is set to current. And so that's a convenient way for you to preserve old versions. And so every version you've ever built will be kept on the system, and it will be available for you to go back to and choose and run anytime. This is very useful for repeatability. And for developers, that's a particularly important thing to have available. If you want to do housekeeping, there is a version, I think it's del or delete, I don't remember which one it is. But of course, the subcommand version has a help. So if you just type in Gridlab-D version help, you'll be able to see what commands are available. There's a few other commands that are available, but these are the important ones. Okay. Just so you know, there's a lot of other make targets that are available, and those targets include things like cleaning the intermediate files. As I said, the build can take a lot of space on your disk. If you do a clean, it gets rid of all those intermediate files and can save you quite a bit of disk space. Build WC, make WC will actually return your repository back to the original clone state. So all files that were created as a result of all of these steps that we've gone through will be removed. One big caveat of using this is if you created a new file and you haven't yet committed it, this command will delete it. So if you're developing, trying to create something new that you want to add, be sure to commit it, add it and commit it before you do a clean WC, because it'll be deleted otherwise. Everything that's not part of the repository will be removed. Index, weather, library, and template are basically things that maintain the cache on your system. So when you build a new system, you need to have an index of the weather library, the libraries, object libraries, the templates. And so you can get those all pre-indexed, which will improve performance later when you're running Gridlab-D. And in fact, these are done automatically when you do a make install to make sure that all the cache indexes and everything are up to date. As I said, make reconfigure is a very useful target when you change version. Anything that changes the name of the target will require reconfigure. If you do make reconfigure debug, it'll turn on debugging options, which is quite useful if you're having problems with Gridlab-D crashing and you want to know why. Uninstall will remove it, obviously. And the remaining ones, HTML, module HTML, developer HTML, troubleshooting HTML, just build a lot of the HTML files that are used as part of documentation to the system. Those are not critical, and they are, for the most part, built automatically anyway. But if you do change any of the source code and you change the internal documentation in the source code, the automatic documentation, and you want to just check the documentation without rebuilding the source code, you can use these targets to avoid doing a full rebuild, which could take a long time. These targets are usually very quick. And a lot of the times when we're doing developer documentation, we just want to double check that there's no typos, that it's formatted correctly, and that should not require a full rebuild. So these targets are useful. So with that, I'm going to pause here, and if there are any questions, I'm going to pause the recording and all right, we're back. Let's continue. So the next step is probably the most lengthy step, and certainly the most challenging. It's the one where the most work has gone into the system itself, and it's a very important step. This is the validation test. There are a lot of components in Gridlab-D. I guess it's got a lot of moving parts. And this validation test is quite comprehensive. It goes through a large number. It basically goes through every portion of the source tree, looking for files that have a very specific name, in folders that have a very specific name, and verifies that the software functions appropriately by running a model for each functionality that we are concerned with testing. And as you can see, so this is the command that you run to do validation testing. It's just a command line option, Gridlab-D -- validate. You can also get this by doing a make validate as well. But this is typically how most people do it, I believe. Certainly how I do it. And that validation test will then go through each file that it finds and run that Gridlab-D model. And if the run is successful, it will report. Well, let me be careful about that, because some of the tests actually should fail. And if so, when I say if the run is successful, it means that the test turns out as expected. Successful runs complete correctly, and unsuccessful runs do not complete as expected. They do not complete, which is what they're supposed to do. And we'll talk about that in a little bit of detail as we go on. But let me just, so basically the validation process runs through all of these models and then reports the success rate. For a Gridlab-D installation to be validated, it must have a 100% success rate. There can be no failures. Currently, there's over 700 tests run. And then depending on your system and how you set things up, that test could take anywhere from 60 seconds to 10 or 15 minutes. It just depends. The testing process can be parallelized. This -T option allows you to specify how many threads you want to use. If you specify a non-zero number, it will use exactly that number of threads. Hopefully you have that many on your system. If you don't know how many threads are on your system and you don't mind committing them all to the validation process, you can use the value 0, which basically says use as many threads as you can create on the system without overloading the system. And so if you have, for example, 8 CPUs on your system, then it'll run 8 simultaneous validation tests at a time. And as soon as one of them completes, it'll start another one and keep all 8 processors fully loaded. So this process does take a fair amount of time, and the results, when they are not successful, have to be investigated. So let's kind of go through what's going on. So the first thing to know is that the test names, the file names, always start with a folder called autotest, and it can be anywhere in the tree. And then the file name has to begin with the word test_, and it has to have the extension GLM. Anything else in between is allowed, with a couple of exceptions for special cases. If the name includes _ERR in it, then the test actually must fail to pass. In other words, we want to verify that something doesn't work that's not supposed to work. So we create an error test. The test, when it's run, if it succeeds, that would be considered a failure of the test. And if it fails, that would be considered success of the test, which is, it's weird. Basically what it does is it allows us to verify that things like syntax error checks work correctly, or inability to solve a problem that has, a particular characteristic can be verified. So you can imagine, for example, if you try to invert a matrix that is, got a zero determinant, that should be an error. So one test you could do is create a problem that has a matrix that inverts to, can't be inverted, and you would expect an error to occur. And so you would name a test like that _ERR. Another special name is _OPT. Basically means optional, which essentially means it's not going to do it. It will ignore that file. It won't run anything, and the test will fail. So these file names are special. The other thing that's important to know is that in order to keep test files with each other, any supporting test files should be named similarly so that they can be kept together when you list them out. You don't have to do this, and you'll find, for example, that a lot of tests don't do this, but we've been trying as much as possible to keep the files that support the test, any CSV files or other supporting files, that they have the same name. So that's basically an overview of the file naming convention. I see there's a question. Where are these 712 models present? Oh, the models are all in these Autotest folders. So, and there's, as I said, they're scattered around in the source tree. So if you were to search your source tree for folders called Autotest, you'd find all of these GLM files. There might be more than that. Well, it depends on the branch. Some branches will have more than others. So now, sometimes we want to disable the validation testing in a particular section of the source tree. So what validate does is, as it searches a source tree, if it encounters a file named validate.no, it will stop searching that source tree and continue elsewhere. Keep searching the remainder of the tree. And so that's a way of disabling validation tests in sections of the source tree for whatever reason you might have. And finally, as I mentioned, the validation output, which is a very detailed summary of each, basically each test, how long it took, what the result of the test was, and then the overall testing result summary for the entire sequence. Those will all be stored in this validate.txt file in the folder where you started the test. One important option that's available to you is to request testing only in a particular folder. So if you use the Gridlab-D -W option, that sets the working directory for Gridlab-D when it starts. So you could, for example, force it to test only the modules by saying -W module. And then only the modules will be tested, and all the other folders will be skipped. And then the result of the validation test will be stored in the module folder itself. So that's a handy way of just checking one thing or one section of the source tree so that you don't have to wait for the entire test sequence to be completed over the entire source tree. Each test has to run in a folder. And so what happens is that Validate creates a folder by the name of the GLM file. So it takes the Autotest folder and the test file name, and it creates a folder by that name. It copies the GLM file into that folder, and then it runs it in that folder. What this means is that if you're referring to any files in the parent tree, you need to conditionally get to those files. Many Autotests do this, and you can see the method for doing that in those Autotests. So I'll suggest, if you run into that situation, all you have to do is find another Autotest where that's done. But basically the trick is to set an environment variable that looks to see if the file that you're interested in exists in the current folder, and if it doesn't, look for it in the parent folder and then use that one. So that's how you conditionally refer to parent folders. So the validation process outputs all of these different files. So each stream in Gridlab-D is sent to a different file. The most important one, obviously, is the error stream. That's where standard error is written to. But if there's any debug output, any information, any other general output to standard out, any progress output goes to the PRG file, any profile output goes to the PRO file, and all the warnings go to the warning WRN file. And then if you're doing end of test difference checking, so for example, you output a file in your test folder and you want to compare it to the original or expected file in the parent folder, then those would be stored in the DIFF output file as well. So that's generally how validation works. On GitHub, validation tests are automatically triggered for any change to the master or develop. So if you make a pull request to develop, that would result in a run of that pull request to make sure that it can be committed to develop. And any change to develop would also run a test to see if it's ready to go to master. And then, of course, any change on master would run a full master actions. And so these actions almost always include full validation checks. And if you go on GitHub and look at the actions tab, you'll see all of the validation tests that are most recently run. And then anytime a validation test fails, it will create a validate result.zip file. That zip file will contain all the folders that have any errors in them. And of course, you know, at least for me, the first stop is always to look at the ERR file, because that's where the evidence of the error will be stored. But the other files may contain interesting and useful information. And then, of course, all your intermediate files will have been output to that folder as well. So if you download this zip file and you go and you try to run the test file that's in there, you may be able to reproduce the result and figure out what the cause of the error is, or turn on debugging, do things like that to try to diagnose the problem. Generally, the error is enough to tell you what's gone wrong and makes it fairly easy to fix the problem. It's not unusual for a validation test to pass locally and to fail on GitHub. GitHub is a slightly different environment from your local environment, and so things may work a little bit differently on GitHub, and so that's not an unusual outcome. Here's what a validation result looks like when you download it. So this is a failure of a tool called Meteostat, and that failure is a result of running this GLM file. And as you can see, the error file is non-empty. It contains a string of some kind, some information related to what the error is. And so inspecting that file would allow you to figure out what the cause of the error is. And if you have multiple errors, you know, then they will be stored in folders. This is essentially a replica of the source tree, but only the portions of the source tree that contain things related to validation errors. It's not a complete copy of the source tree. So you can see here's the tools folder, here's the Autotest folder, here's the test folder for the Meteostat tool itself, and then here's the contents of that folder after the test failed. So general guidelines for validation tests. They're designed to test every major functional portion of Gridlab-D. They're supposed to be quick, and they should run very quickly. Some of them do not. Some of them are actually very lengthy and can take more than a minute to run. Those tests are fairly rare. There's only a few of those. What we try to do is move those to the front as early as possible in the test sequence, so that if you're running a parallel test, they don't affect the overall parallel runtime very much, because you're able to get all of the quick tests done using the other CPUs while the slow tests are being run on a few of the CPUs. Generally, what we try to do is have the validation tests run a realistic scenario. There's a couple of advantages of doing this. I mean, obviously, using a realistic scenario means that we're most likely to catch situations where users would do things that might cause the system to break, and we want to detect those before the user gets their hands on the system. The other advantage of this is that validation tests are actually really good examples of how to do things. And so I find myself, when I don't remember how to do something, I actually, just as often, I'll go to the validation test for how to see how it's done, because the validation test shows how to use all the different options. The documentation is not always great at giving examples of how to do things, but the validation tests are very good at doing that. So one thing to remember when you're creating validation tests is you should create both positive and negative tests. So you have to test not only the functionality that should work, but you should also test the functionality that should not work. As a result, this means there's going to be a lot of tests, right? If you think about one particular command, that command might have 5 or 6 options, and each option might have 3 or 4 ways you can use it, and then a couple of ways you can't use it. So you have to create a validation test for each of those. You might want to group all the positive tests together into one test that does them all one after another. But as far as the negative tests are concerned, you have no choice but to do each one independently, because you're supposed to verify that they all fail, and that might be difficult to do with a single test. So those typically can be numerous, but they also typically are very quick, because failure is something that you should generally detect easily. One huge caveat with validation tests is do not do validation tests that require credentials. The infrastructure for HiPAS Gridlab-D in GitHub currently does not have very good support for tests that require credentials. This is something we're working on, but under no circumstances should you put personal credentials into a test in order to complete the test. That's going to cause all sorts of problems, up to and including, having to reset all your credentials, getting nasty messages from GitHub and from whoever else the credentials might be watched. We've run into situations where AWS has sent, Amazon has sent us, nasty notes about credentials being revealed in a pull request. This is something you don't want to do. And so because in the course of development, we tend to want to, sort of get the work done, there's a tendency to put the credentials into your source code and say, oh, I'll get around to that later. Well, sometimes you don't get around to it later, and then you make the pull request and then it's too late. So my suggestion is if you do have tests that require credentials, do it properly right from the beginning. And we'll talk about how credentials are handled in Gridlab-D in a minute. But don't take shortcuts. Just do it right the first time. There's just too many ways to have accidents and things go wrong if you take a shortcut early on. It's not worth it. So just get in the habit of doing it correctly. You won't regret it. Another thing that's really useful, and I'm going to recommend everyone do, unfortunately, not every validation test in Gridlab-D does this right now, is to use what's called a termination check. And in a termination check, what you do is you add a test that allows you to verify whether or not the file that you've created matches the file that it's supposed to look like. So when you create an output file of some kind, you want to make sure that it matches the original. And this is really common in a test, right? You run some kind of a process, it produces an output. You want to make sure that that output is correct. Well, the best way to do that is to just match it against something that you've already generated. And so you'll have to forgive me, there's a typo here. It's missing a ... / in front. But basically what you do is you check to see if the original exists. And if the original exists, you check the difference between the original and the new one, and you store that in the diff file. I'll correct this error, this missing ... slash up here on the if-def on the slide deck when I post it. My apologies for that. But this kind of termination check is really useful. You can also do a termination check on a failure just by using an onExit -1, which basically means if the run fails, do some kind of a check, although obviously, you would expect this failure to result in a failure, so that would be fine. But maybe there's other kinds of failures you want to detect in the simulation, in the validation test, and those you would capture with an onExit -1. So these are really useful things to do. There are other ways of checking for errors in simulations, but this is probably the most common one. All right, I want to talk a little bit about the converters in Gridlab-D. There's quite a lot of converters now part of the distribution of Gridlab-D. And these converters are automatic on input and output. So if you tell Gridlab-D to read a file and the file isn't a GLM file, then it will try to run a converter to create a GLM file that it can load, because Gridlab-D doesn't actually know how to load any of these files, but the converters can create a file set that Gridlab-D can load. Now, the problem with this is that just the file extension isn't enough to tell you what to do. So there's two parts to conversion, automatic conversion. One is the part that identifies the extensions from and to that you're converting. And then the second part identifies the semantics associated with that extension. So is it a CSV file containing weather data, or is it a CSV file containing power SCADA data, and so on. So there are different semantics associated with different extensions, both on the input, which is called the type, and on the output, which is called the format. I should note, this is potentially confusing, because if you think about the first letter T, you might think of that as to, and the first letter F, you might think of that as from, but that's not the case. T and type mean input, and F and format mean output. So the options to the converters allow you to specify the semantics. Gridlab-D will take care of that automatically if you tell it what kind of input type you're dealing with. And when we talk about converters in a future session, we'll talk about that in more detail. At this point, this is really only relevant from a validation perspective, just to let you know that the validation tests do use the converters and test the converters, both on the input and output. The internal converters in Gridlab-D, going between GLM format and JSON format, are also tested, but because they're internal, they're also used in almost every other test. So generally, these internal converters are very well verified and tested. If an error occurs in either of these, it's almost certain to break all the converters. So if you're working on either of these formatters in the internal Gridlab-D, and you see all the other validation tests or many other validation tests fail, it's almost certainly because something's gone wrong in these internal converters. Otherwise, the validation tests for specific input and output converters are present, but I should say not all of them have been tested, are being validated. Many of them are being used as convenience converters in other tests, but they don't have their own direct validation test. I would consider that a bit of a deficiency and something that we should probably address. When we get to the homework assignment, I'll talk about that a little bit more. The other thing that happens with converters is because a lot of the files that we want to test come from utilities and are proprietary, those files are not included in the standard testing procedure for Gridlab-D. Those are included in private repos that belong to the utilities or belong to Slack, where it's been given permission to use them, and they are not available to all developers. So it is quite possible that as a developer, you might work, for example, on an MDB converter change. implement it, and it passes all of the tests in Gridlab-D's standard repository, and yet you get a notice from us saying you broke the converter because we ran one of the private repos and detected a problem. If that does happen, don't worry about it. We will take care of it. Those of us who have these private repos have basically assumed responsibility for maintaining compatibility. And until those test files are made public, there is no other way to deal with it. You won't be asked to fix something you can't see. Those of us who own the private repos with the test files that caused or detected the problem, we will deal with the consequences. So don't worry about it. But I just want to make sure everybody knows that there are many of these private repos with files and data sets that are used to test Gridlab-D that could result in validation tests not passing that you would never see, and we'll just deal with it. What generally happens is that when you submit a change for review by the Gridlab-D management team, that's when we run these private tests, and that's when we might detect something like that. And then we'll either propose a change on the pull request, or we might accept the change into develop branch and then make our own fix separately, so that you won't even see the change made to make the private repo work. Anyway, that's a big caveat related to the converters. It's something that we've just had to deal with, given the fact that there are far more private repos with data sets that we use to test Gridlab-D than there are public ones. There are literally thousands of models that we have in our private repos that we use for testing that cannot be used, revealed publicly. The second thing that's special about validation relates to geodata. The geographic data sets use a non-standard from the Gridlab-D perspective, testing mechanism, in that they use the built-in unit testing that's available in the unit test package in Python. So what happens is that there's a single GLM file that that basically starts up the geodata testing script and tests all of the geodata packages individually using this unit test mechanism. What this means is that people who implement geodata packages have to actually implement these test classes themselves and generate all the tests in Python rather than in Gridlab-D models. There's really no way to directly test geodata in Gridlab-D comprehensively. And so it's done using this unit test mechanism. This technique may actually become more common as Python packages become more widely used in Gridlab-D. But geodata is the only place where Python is required and not simply an option. The entire geodata package is implemented in Python. You can't use shell scripts. You can't use any other language. That's the only language that's allowed at this point in the geodata package. So we use Python's unit testing mechanism because it's very good and very well supported, and allows us to do much more detailed unit testing than we could do with GLM files. And so that's sort of one idiosyncratic thing about validation testing. Some subcommands can also be validation tested, but some of them are extremely slow. So there's a matrix subcommand that allows you to prepare data for Gridlab-D, basically formatting CSV data that is presented in the form of a matrix and allowing you to manipulate it. So the matrix auto test is comprehensive. It tests all of the matrix commands that are available. And there are, I don't know, it's like maybe 40 or 50 of those commands that are supported, might be even more than that. So that test takes quite a while. And as a result, if you're running just one processor, you could spend a lot of time waiting for that single matrix test to finish. Some of the other subcommands are not tested at all. So they're missing auto tests. At some point, someone will have to create an auto test for that. And again, I refer to our homework assignment at the end. They're not, it's not that big a deal that they're not auto tested. First of all, they're very simple. In some cases, they simply pass through to other things that are auto tested already. So that shouldn't be an issue. There are things that, it's just really obvious when they don't work, and we'll catch it anyway. There are also commands that are sensitive to version changes in the packages that support them. Auto tests are a little tricky then. And we have some mechanisms for testing different versions, but it's not yet been very well implemented. And so we find that these auto tests fail frequently, and we've either disabled them or kept them really trivial so that we don't constantly get failures when we don't really have something to worry about. And so this includes the pandas subcommand, which is used for manipulating tables, the OpenFIDO command, which is used for accessing OpenFIDO's workflows and using those as part of Gridlab-D models, and then the plot subcommand, which allows you to take Gridlab-D output and generate plots. So these are rather version sensitive to Python, changes the Python version, and so it's just something to be aware of. And then there are some auto tests that are just flat out not possible, or some subcommands that are flat out not possible to auto test because they essentially are user interface subcommands. Trace is a good example. When your system crashes for some reason, you can use the trace auto command, the trace subcommand to find out why it crashed. There's no way to use that in an auto test because it goes into the debugger and then it does stuff. And that's just not something that's really easy to auto test, and so we don't. Unfortunately, what that means is that when trace breaks, we don't have a good way of detecting that. So until somebody uses it and notices that it isn't working, it's not easy to tell that the trace command isn't working. Tools are often difficult to auto test because of credentials. We try as much as possible to create pathways for tools to work without credentials. Usually that's done by putting a copy of source data or test data on AWS S3 buckets. So that's a way of doing it, or we put the data into a repository that's available to the public. So that's just something to be aware of. It's important to make sure that your auto tests don't use credentials, but sometimes it's not always possible to test the pathways that make credentials work if you can't include credentials. As I said, we're working on ways of allowing us to include credentials for these kinds of tests to run both in GitHub Actions and elsewhere, but we haven't resolved this problem yet completely, and so we're just going to hold off on that, and we'll let you know once we figure out exactly how we think credentials should be handled, both in GitHub Actions and in your own repositories, to be able to test different tools. The other thing that we've noticed is that some tools will just fail for no apparent reason. This is particularly true for tools that access network resources. And we think it's just because network resources will occasionally be overloaded or temporarily unavailable. Docker might be unavailable, or one of the repos might be temporarily unavailable. And so the test fails. If it fails on GitHub Actions for no apparent reason that you can figure, just rerun it. And sometimes it'll pass, and then that problem just never happens again. If it continues to fail, then maybe there's something really going on. But generally, a rerun makes the problem go away. It's not super reassuring when that happens, not having a good explanation of why it failed. You can try adding more diagnostic information to the error message to trace back, for example, in Python is a good idea. Turning on debugging in a Gridlab-D model can help. Verbose and debugging can both help identify the source of the problem. But yeah, typically these kinds of errors just don't repeat, and you know, there's not much you can do about it. The other thing we've noticed is that parallelism in your validation tests can be an issue if you don't implement file sharing correctly in your tool. So a good example is if you have a tool or a set of tests for your tool that store files in, say, the temp folder, and they're all using the same folder, and they're presumably using the same, they might even be using the same file names for operations, they can interfere with each other. So you really need to be careful in implementing your tools to make sure that you're aware of parallelism, and that when you are manipulating files that could be shared across multiple runs of the tool, that you do so in a file sharing friendly manner. This may mean you have to introduce locking, or you have to guarantee unique file names, things like that. This is something that we often don't think about when we're implementing a tool, and then when that tool gets tested in parallel, that problem crops up, and it could give rise to intermittent errors, because it really depends on whether that particular clash on a file name or a folder happened in exactly the same way repeatedly, which is very unusual. It would be very hard to guarantee that it always happens repeatedly the same way. So this is, again, a source of potential intermittent problems, and so you should consider being very careful about how you create temporary files or files that are shared across multiple instances of the tool. Okay, so running on Docker is a really common thing, and I just want to kind of quickly go over some key concepts when using Docker. If you want to build a Docker image of Gridlab-D, you should go into the Docker folder and just do docker build dot. That's the standard way of building the master image. If you want to build a branch image, you just have to give the build argument branch equals and then the name of the branch, like develop or whatever your branch name is. And that would be sufficient to cause it to build that specific branch. If you're using a different repo, you're not using the standard repo for Gridlab-D, then you may have to provide additional information to identify the repo and so on. You can find all of that information in the Docker build file that's in the Docker folder. Once you've done that build, you can get a list of the images that you've built, and you'll see generally it's the top listed image, the most recent one you've created. And then you can just run that image with this command and you can validate it. So the image ID is shown when you get a Docker, when you run the Docker images command. And then if you do a Docker run, you want to run an interactive terminal with a volume that's mounted to the temp folder, because that's the default folder that Docker uses. So you want to take your current folder, mount it on temp, run the image that you just created, and then run the validate command from that folder, and it will validate that image completely. Once the image is validated, you can just run, use it, and yeah, it's basically a totally runnable image. If you want to mount volumes for your own models, you can do that the same way. Be careful about running in the temp folder, because a lot of other tools use the temp folder also, and it's possible it would clash. But generally it's not much of a problem. But if you do run in a different folder, you'll have to use the -w command to move Gridlab-D to that other folder. So for example, if you say use model instead of temp, then you would do Gridlab-D -W model validate, and that would move Gridlab-D over to the folder that's mounted as your volume. So that's a really convenient way of using the tool. The nice thing about using Docker is we've created a bunch of images that are standard and they're preserved, for posterity. And so if you are using an image and an image on Docker, you can basically be assured that you're getting the same image over and over again when you go to run future versions of your model. This is how you maintain repeatability. This is the first step in having highly repeatable results coming out of Gridlab-D. AWS is similar in concept, but you have to create your own AWS instance. We know the free tier T2 micro instance works. It's obviously very quick to create. You can create an instance in just a few seconds. What we've noticed, though, is that if you run Gridlab-D on a T2 micro, usually it's pretty slow. The T2 micros don't run very fast. They are free. That's, I guess you get what you pay for. Now, if you want a good AWS EC2 instance, T2 large seems to work pretty well for most simple, quick tests. And so that's typically what I use for my testing purposes. When I'm doing normal development work, I'll use a T2 extra large. So that seems to be ideal for most purposes. We have used in production all the way up to, as I said, a C5A 24X. So that's a really big system. I think it's 96 processors with, I think it's 256 gig of RAM, I believe. I'm not positive. It might be 192, but anyway, it's big. Those 96 processors, you can run, for example, a validation test on those 96 processors, and it will go very, very quickly. Basically, it will take just about the amount of time of the longest test takes to run on that system. So, and I don't remember how long the longest test is, but it's something like 60 seconds. And so if you're doing very large production runs where you have to run, say, thousands of simulations, then these systems, these AWS systems, are very effective, and they're very cost effective. We've done, multi-thousand simulations, annual feeder simulations for load forecasting on a system like this, and been able to complete the run in a few hours. And so that's a very good platform for doing that kind of thing. So the overall preparation is exactly what we talked about earlier. You just run the install.sh script on the new EC2 instance. The specific one that it will run is Linux Amazon 2, and it will set your system up. You can then save that AMI if you want. There are AMIs already published on AWS. And if you just, when you're building your instance, if you just search for the keyword Gridlab-D, you'll get a list of all the public AMIs that are available. And we try to keep the most recent one up to date, so you can see the ones that we've built recently. And of course, if you build your own and you want to share it publicly, that's something that Amazon encourages. All right, so a few tips and tricks before we wrap it up today. The first thing is, when you clone Gridlab-D, you can speed up the clone and go directly to a particular branch by specifying the branch name and the depth of the clone. That will make it go very quickly and make it unnecessary to do any kind of a branch change later. You'll just get exactly what it is you want right out of the box. Another useful trick is, if you have Docker, but you've also built locally on your system, you can ask Gridlab-D to enable the Docker image to be your default Gridlab-D run from your local host. And so you just tell Gridlab-D to enable Docker on the image that you want, and it will pull the image if you haven't already done so, and it will use that instead of the normal Gridlab-D that you've installed on your local system. Don't forget to disable Docker before you do anything with your local system. In particular, if you don't disable Docker and you try to build Gridlab-D with Docker enabled, and you try to build your local Gridlab-D, it gets really confused because it can't tell which one it's trying to run as it's trying to set the version, and it might not set the version correctly. It's probably something we could fix, but we haven't figured out exactly how to fix that yet. So just remember to disable it if you're going to resume work on your local installation. Another thing to remember, and I mentioned this earlier, is if you change your branch, make sure you reconfigure and do either a make install or make system. And then of course you can clean up all of your source code. You can either do a make clean WC or directly run the utility clean WC, but just be careful not to lose your local work. I can't stress that enough. I've done it. It's very disappointing when it happens. Yeah, you will lose your work, and there's no way to recover it unless you happen to have made a copy before you ran the command. Another thing that's done as part of the build process is cloud deployment. And specifically, this addresses deploying the S3 buckets that support some of the URLs that are used in the code. So there's a code URL, which allows you to retrieve files directly from the repositories inside Gridlab-D. A docs URL, which is the URL that is used for the online documentation. It's also where you will be pointed if you request help on something online. The geodata URL, which contains all of the support files for the geodata tools, packages. Status, which just gives you the overall development status of Gridlab-D. Tutorials, where these and other tutorials will be stored. And then there's the general landing page for Gridlab-D itself. There are two variants. There's the actual URL, and then there's a dev variant. Only the master produces the actual URL. All other development branches will produce a dev if you do a make cloud. So do keep in mind that you're sharing that dev with everybody else. It doesn't make, we don't have multiple dev ones. We have just one that are shared by all development branches. So yes, it's quite possible that your development work could interfere with someone else's development work if they happen to be making changes in the same place. At this point, we don't have a good way of managing that, but maybe someday we'll come up with something clever that we can use to manage that potential conflict among the developers. There aren't that many of us at this time that I'm overly concerned about it, but at some point, I imagine it could happen. The other thing to keep in mind is that although the makefile does directly support Azure and Google Cloud resources, we don't actually have any in our build process at this point in time. I'm expecting we will at some point. We just haven't had any created yet. Everything we need is supported by AWS and is shared by everybody, and so that's fine. Cache folders, I mentioned earlier that we have a variety of folders that are created during the installation, and that some of the installation does indexing and downloading of files that are useful. Those are all stored in the share folder called Gridlab-D. During runtime, Gridlab-D uses the GLD_etc environment variable to tell every tool where the share is. And so you can use that to identify, for example, the weather cache, the templates cache, the library cache, or any other cache that you might want to create for your own tools that you want to share with other users on that system. All these, of course, are local to your host. And of course, the cache can be cleared relatively easily, either by your own tool or by directly removing the cache folder in the shared folder itself. I mentioned before credentials. You can store your own credentials locally, and those will never be touched by any part of the Gridlab-D installation. It's basically off limits for Gridlab-D installations to look at the home.aws.github.nsrdb and any other credentials that you might have. But it's not uncommon for tools to go and look at those credentials because it needs to use them to log in, but never will those credentials be copied any place where they might be revealed to other users. That should never be done. So you should be very careful when you're looking at these credentials files that you do it as a read-only operation and that you never write those any place other than handing them off to the library that needs them for access. So that's just, it's a fairly simple thing to do to read these, but you should be very careful never to print them, never to save them anywhere else, never to put them in logs, things like that. Okay. Finally, online documentation. As I said, it's stored in the docs folder. It uses a document browser that was created for all of Slack's tool development. If you don't log in on GitHub, you have a rate limit. It's a pretty good rate limit. You're not going to run into it too often. But if you do run into it, you just need to go get a token from your GitHub account and give that token to the docs browser, and then you won't be rate limited. Well, you still have a rate limit, but it's like 100 times what the normal unauthenticated user has. Just some quick things about GitHub itself and the docs files. There's a couple of key strings that you can use to get images or YouTube videos or take code directly from a GitHub repository to help with your documentation. Of course, the usual markdown for links is just to put the double bracket, except that the document name is the full path in the docs folder. And then if you want to create a button using a document, you just use double parentheses. So those are nice little tricks for making your online documents look nice. The documentation template is provided. I typically just go and copy a similar document and then modify it. But generally, we have a synopsis that has either the shell, GLM, or Python syntax in it, a description, a list of all the options, an example, any caveats that might come up, and then the see also list. So this is typically the way it looks. This first item here is how it will be referred to by others, and it should be shown in that form as the first thing in the file. And by the way, if you have a to-do, capital T-O-D-O, anywhere in the file will be flagged as having to-do items. And if a user looks at it, they'll get a little warning that says there are to-do items in the file, that the documentation is potentially not complete. So this is what it looks like when you look at it from the user's perspective. The synopsis contains basically all of the information pertinent to using it, and then the general description and so on is listed below. This is what buttons look like, so there's a nice handy way of providing them. And then there's just general tools for reporting a problem or editing the document itself. If there's a problem, that edit will result in a pull request back to the develop branch. Actually, yeah, I think it'll go to the develop branch. And of course, you can just link directly to the source code using that. Generally, the project is always the Gridlab-D project, although you can change it to any other project in any other organization. So you can use this to browse any documentation anywhere on GitHub. And then you can look at the documentation to a specific branch, which is what's so important about this documentation tool. It allows us to review documentation and have some assurance that it looks the way we want it before it's released to the master branch along with the source code. If you're making contributions, this is the overall flow. Only the master release is used to produce versions of Gridlab-D. Develop branch is used to make changes into the master release. So pull requests are there's always one pull request from develop into master, and that's the main pull request for the next release. And then either in the organization, the HiPAS itself in GitHub, we have branches that are named develop-whatever. Actually, it could be named anything, but we have a sort of convention that we always use develop, because that allows GitHub Actions to test the branch. And then forks should either go to a branch that is pending being merged into develop, or directly into develop if it's ready. And that's kind of your call, how you want to do that. Yeah, this is the general overall process. So you can fork the HiPAS version. Right now, there's a Slack Gizmo fork, and actually they're swapped. the relationship is swapped, but we're about to change that. HiPAS will become the primary branch through which all releases will be made. So all of your contributions should go in through pull requests. Please keep your branches up to date using merges from develop. If you don't, your pull requests will get unwieldy and potentially impossible for us to accept. And then your pull request should be reviewed by one of the administrative team, myself, Alona, or others who are able to do pull request reviews into the develop branch. All right, so that wraps it up. I'm going to tell you what your homework is before I open it up for questions. So your homework assignment for next week is to fork the Slack Gizmo branch, because it happens to be the one that's currently the primary branch. Later on, it'll be the HiPAS branch, but it won't matter because we'll keep Slack Gizmo up to date anyway. Fork that branch into a repository that belongs to you. Find some particular functionality for which there is a missing or incomplete validation test. So you have to look through and see if look through the validation test and find something that's missing. And either create a test if it's missing, or if it's not a good test because it doesn't actually do a final check or a a verification of some kind, make it one that actually checks something. We know that there are still validation tests out there that are either incomplete, or there are functionalities that are completely absent, missing a validation test. So find one and fix it. And if you're successful in doing that and getting an auto test and getting it to run, submit a pull request to us, and we will merge it at some point into the develop branch and make it part of the system. So yeah, your first homework assignment is to do our job for us. I heard recently, actually this morning, that Apple does this as part of their interview. You actually do work for them. So it's, yeah, I think it's a very valuable exercise. You will learn a lot about how validation testing is done. And you will learn a lot about how to build a system and to go through the whole process. And you will be helping the project overall as well. So we appreciate that. So I think with that, I will leave it and go into questions. What I will do is stop the recording so that we close it here and then go into our questions.